Hello, my name is Shabsina and welcome to my channel. So in this previous video we have learned about the types of tree. Now we will the tree and its introduction. So in this video we will learn about the types of tree in a more detailed manner, right? So first of all, binary tree is an example of a tree data structure. So let's see it. So what is the introduction? Basically, the binary tree means that the node can have maximum 2 children. We can say that the name itself suggests that 2. Therefore, each node can have either 0, 1 or 2 children. So, this is an example of a binary tree. So, let's understand the binary tree through this graph. This tree is a binary tree because each node contains the utmost 2 children. So we can say that the left and the right pointer pointing to the left and right node respectively. The node 2 contains both the nodes, left and right node. Therefore, it has 2 pointers, left and right. The nodes 3, 5 and 6 are the leaf nodes. So all these nodes contain null pointer on both left and right parts. So this is the representation which I was talking about, that in this example you can see that node 1 contains 2 pointers, that is left and a right pointer, right? So the left node the node 2 contains both the nodes, that is left and right node. So therefore it has 2 pointers, left and right, and the nodes 3, 5 and 6 are the leaf nodes. So all these nodes contain null pointer on both left and right parts. Now, the properties of binary tree. At each level of I, the maximum number of nodes is 2 to the power I. The height of the tree is defined as the longest path from the root node to the leaf node. The tree, which is shown above, has a height equal to 3. Therefore, the maximum number of nodes at height 3 is equal to 1 plus 2 plus 4 plus 8, which is equals to 15, right? In general, the maximum number of nodes possible at height is 2 to the power h plus 1 minus 1. The minimum number of nodes possible at height h is equals to h plus 1. So, if the number of nodes is minimum, then the height of the tree would be maximum. Conversely, if the number of nodes is maximum, then the height of the tree would be minimum too. And now, if there are n number of nodes in the binary tree, the minimum height can be computed as h equals to log 2 of n plus 1 minus 1, and the maximum height can be computed as h equals to n minus 1. Now, the types of binary tree. There are 4 types of binary tree. First is full or proper or strict binary tree. Second is complete binary tree. Third is perfect binary tree. Fourth is degenerate binary tree, and the fifth one is balanced binary tree. So let's see those types of binary tree in more detailed manner. First of all, what is the full, proper, strict binary tree? The full binary tree is also known as a strict binary tree. The tree can only be considered as the full binary tree if each node must contain either 0 or 2 children. The full binary tree can also be defined as the tree in which each node must contain 2 child children except the leaf node. So let's look at this example. So in this tree, we can observe that each node is either containing 0 or 2 children. Therefore, it is a full binary tree. Now coming to the properties of full binary tree, the number of leaf nodes is equal to the number of internal nodes plus 1. In the above diagram, right, in here, the number of internal nodes is 5. Therefore, the number of nodes is equal to 6. So, the maximum number of nodes is the same as the number of nodes in in the binary tree, that is 2 to the power h plus 1 minus 1. The minimum number of nodes in the full binary tree is 2h minus 1. The minimum height of the full binary tree is log 2 n plus 1 minus 1. The maximum height of the full binary tree can be computed as n equals to 2h minus 1. And finally, n plus 1 equals to 2h and h equals to n plus 1 by 2. Now, coming to the complete binary tree. The complete binary tree is a tree in which all the nodes are completely filled except the last level. In the last level, all the nodes must be left as possible. In a complete binary tree, the nodes should be added from the left. So let's look at this example, that the above tree is a complete binary tree, this one, because all the nodes are completely filled and all the nodes in the last level are added at the level first, right? So coming to the properties of a complete binary tree, the maximum number of nodes in complete binary tree is 2 to the power h plus 1 minus 1. The minimum number of nodes in complete binary tree is 2 to the power h. The minimum height of a complete binary tree is log 2 n plus 1 minus 1. And the maximum height of a complete binary tree is h equals to n minus 2. I forgot to write the maximum height, so please excuse me. So coming to the perfect binary tree. A tree is a perfect binary tree if all the internal nodes have 2 children and all the leaf nodes are at the same level. So let's look at this example of a perfect binary tree. The below tree is not a perfect binary tree because all the leaf nodes are not at the same level, right? So example of a perfect binary tree, this one. So this tree we can see that all the leaf nodes are not at the same level. So that is why it is not a perfect binary tree. And this one is a perfect binary tree because all the internals have 2 children and all leaf nodes are at the same level, right? The leaf nodes, which I mean to say that 4, 5, 6, 7 are known as leaf nodes and they are all at the same level. But here you can see that 2, 6, 7 are not at the same level. That is why it is not a perfect binary tree, right? So I must say that I have written it wrong here. It should be imperfect binary tree. Okay, so please excuse me for that also. It should be imperfect. So as you can see that 2, 6, 7 are not at the same level. So now coming to the degenerate binary tree. The degenerate binary tree is a tree in which all the internal nodes have only one children. So let's understand this. So this tree is a degenerate binary tree because all the nodes have only one child. It is also known as a right skewed tree as all the nodes have a right child only, right? See, 20, 30, 40, 50 are all the right child. Similarly, in this case, this tree is also a degenerate binary tree because all the nodes have only one child. But here it is known as a left skewed tree because, as you can say, that all the nodes have a left child only, right? See, 2, 3, 4, 5 are present at the left side. Here it is right skewed tree because all the nodes are present at right. Here it is known as the left skewed tree because all the nodes are present at the left child, right? Left side only. Now coming to the balanced binary tree. The balanced binary tree is a tree in which both the left and right trees differ by at most one. For example, ABL and red-black trees are balanced binary tree. So let's understand this graph. This tree is balanced binary tree. Why? Because the difference between the left subtree and the right subtree is 0, right? This is the left subtree and the right subtree. The difference will be 0. Again, this tree is not a balanced binary tree. Why? Because the difference between the left subtree and the right subtree is greater than 1. Okay, so if I differentiate this, then it will be a greater than 1, right? So these are the examples of binary tree. Now we will look about the binary search tree. So before coming to the binary search tree, let's recap what is a tree. So I have already explained that in a previous video, but let me recapitulate for you guys for one more time, that what is a tree. A tree is a kind of data structure that is used to represent the data in hierarchical form. It can be defined as a collection of objects or entities called as nodes that are linked together to simulate a hierarchy, right? And we should know that tree is a non-linear data structure, as the data in a tree is not stored linearly or sequentially. That's why tree, always remember that tree is always a non-linear data structure, because the data are not stored in linearly or sequentially. Now, what is binary search tree? A binary search tree follows some order to arrange the elements. In a binary search tree, the value of the left node must be smaller than the parent node, and the value of the right node must be greater than the parent node. So this rule is applied recursively to the left and right subtrees of the root. So let's understand the concept of binary search tree with an example. So as you can see, this is an example, right? So in this figure we can observe that the root node is 40, and all the nodes of the left subtree are smaller than the root node, and all the nodes of the right subtree are greater than the root node, right? So you can see that the left nodes, which contain 30, 21, 35, are smaller than 40, obviously, and all the right nodes, which have their data 50, 45, 60, are all the right. Similarly, we can see that the left child of root node is greater than its left child and smaller than its right child, right? See, this 30, 25 is smaller than 30, right? And 35 is greater than 30. So therefore we can say, so it also satisfies the property of a binary search tree. This is one property, that the left child of root node, so in this case, the left child will be 30, in 40 will be the root node, the left child will be small and the right child will be greater than the root node than the value of the root node. So it is a property. So coming to the advantages of binary search tree, searching an element in the binary search tree is easy, as we always have a hint that which subtree has the desired element. As compared to array and linked list, insertion and deletion operations are faster in BST or binary search tree, right? So example of creating a binary search tree. Suppose the data elements are 45, 15, 79, 90, 10, 55, 12, 20, 15. First, we have to insert 45 into the tree as the root of the tree. Then we have to read the next element. If it is smaller than the root node, insert it as the root of the left subtree and move to the next element. Otherwise, if the element is larger than the root node, then insert it as the root of the right subtree. So what will be the step? So step 1 will be insert 45. Second step will be insert 15. As 15 is smaller than 45, so insert it as the root node of the left subtree. We have already see here that it is a property, right? The value which will be smaller than the root node will be inserted at the left side, and the value which will be at the more of the root of the value of the root will be placed at the right side only. Okay. So by following that property, we say that the 15 will be placed at the left side, because the value of 15 is much smaller than 45. Step 3 will be insert 79. So where will it go? It obviously will go at 40, 50, 79. 79 will be placed at the right side, right? Because so insert it as a root node of the right subtree. because we have already seen that 79 is the value of 79 is much more greater than 45. Okay, now coming to the step 4, insert 90. So 90 will be placed at the right side only because 90 is greater than 45 and 79. So it will be inserted as the right subtree of 79. The step 5 will be, after 90 we have to insert 10 and 55. Okay, so the step 5 will be 10 will be inserted after 15 because 10 is smaller than 45 and 15. So it will be inserted as a left subtree of 15. The step 6 will be insert 55, right? Sorry. Right, we have to insert 55 12 here. So now we have to insert 55. Okay, step 6. So 55 is larger than 45 obviously, but smaller than 79. So it will be inserted as the left subtree of 79. So it will be inserted like this. Then I have to insert the 12. So the step 7 will be 12 is smaller than 45 but 50 and 15, 45 and 15 but greater than 10. So it will be inserted as the right subtree of 10 obviously. So step 8 will be insert 20. So what should it mean? That 20 is smaller than 45 but greater than 15. So it will be inserted as the right subtree of 15. Now the step 9, which is the final step, will be the insertion of 50. So as you can say that 50 is greater than 45 but smaller than 79 and 15. So it will be inserted as a left subtree of 55. Okay, so now the creation of binary search tree is completed, and after that we will move towards the operations that can be performed on binary search tree. We can perform insert, delete and search operations on the binary search tree. Okay, so first of all, the searching in a binary search tree. So searching means to find or locate a specific element or node in a data structure. In binary search tree, searching a node is easy because elements in binary search tree are stored in a specific order. The steps of searching a node in binary search tree are as follows. So first, compare the elements to be searched with the root element of the tree. Second one is, if root is matched with the target element, then return the node's location. Third step is, if it is not matched, then check whether the item is less than the root element. If it is smaller than the root element, then move to the left subtree. The fourth step is, if it is larger than the root element, then we will move to the right subtree. The fifth step is, repeat the above procedure recursively until the match is found. And final step is, if the element is not found or not present in the tree, then return null. So coming to the deletion in binary search tree. So in a binary search tree, we must delete a node from the tree by keeping in mind that the property of binary search tree is not violated. To delete a node from binary search tree, there are three possible situations occur. The node to be deleted is the leaf node, or the node to be deleted has only one child, and the node to be deleted has two child, right? Now the complexity of the binary search tree. First one is time complexity. As you can see in the diagram, that the best case time complexity is insertion is O of log n, the average case is O of log n, and the worst case will be O of n in case of insertion. In case of deletion, O of log n, O of log n, O of n only, and in the case of search also O of log n, O of log n and O of n. All the best case, average case, worst case will be remain same in case of insertion, deletion and search. In case of space complexity also, the value will be same. O of n will be the ON will be same for both, for these three operations, same operations, insertion, deletion and search. So now we will come about the AVL tree. After AVL tree, we will learn about the B tree and B plus tree. So and two trees are remaining right now. So what is AVL tree? First of all, I must say that AVL tree is invented by G.M. Adelson. Belsky, and E.M. Landis in 1962. The tree is named AVL in honor of its inventors. Okay, that James and Adelson, Belsky, and E.M. Landis. So Adelson, Belsky, and Landis. So that is why it is known as AVL. This is much more interesting fact. So AVL tree can be defined as high valence binary tree, search tree in which each node is associated with a valence factor, which is calculated by subtracting the height of its right subtree from that of its left subtree. So tree is said to balance if balance factor of each node is in between -1 to 1. Otherwise, the tree will be unbalanced and need to be balanced. Now, coming to the complexity part. So the average case will be O of n, and the rest of the space algorithm, and in case of search, insert, delete, O of log n and O of log n will be remain all the same, right? You can pause the video and can just look and go through it. Now the operations on AVL tree. So in case of insertion in AVL tree is performed in the same way as it is performed in a binary search tree. However, it may lead to violation in the AVL tree property, and therefore the tree may need balancing. The tree can be balanced by applying rotations. So in case of division can also be performed in the same way as it is performed in a binary search tree. Division may also disturb the balance of the tree. Therefore, various types of rotations are used to rebalance the tree. So these are the AVL rotations. Okay, so first one is LL rotation, which means inserted node is in the left subtree of A. The other rotation will be inserted node is in the right subtree of A. Then the third one is LR rotation, which means inserted node is in the right subtree of left subtree of A. And the final one is RL notation, which means inserted node is in the left subtree of right subtree of A. Now we come to the binary tree. Sorry, B tree. Okay, so don't confuse with the binary tree and B tree. B tree and binary tree they have an L&M difference between them. Okay, so B tree is a specialized M-way tree that can be widely used for these accesses. A B tree of order M can have at most M-1 keys and M children. One of the main reasons of using B tree is its capability to store large number of keys in a single node and large key values by keeping the height of the tree relatively small. So we can say that a B tree of order M contains all the properties of an M-way tree. So we can say that it contains the following properties. Every node in a B tree contains at most M children. Every node in a B tree except the root node and the leaf node contains at least M/2 children. The root nodes must have at least 2 nodes, and finally all the leaf nodes must be at the same level. It is not necessary that all the nodes contain the same number of children, but as you know that each node must have M/2 number of nodes. Okay. Now coming to the operations part. So in case of insertions are done at the leaf node level. The following algorithm needs to be followed in order to insert an item into B tree. So traverse the B tree in order to find the appropriate leaf node at which the node can be inserted. If the leaf node contains less than M-1 keys, then insert the element in the increasing order. Else, if the leaf node contains M-1 keys, then follow the following steps. Insert the new element in the increasing order of elements. Split the node into the 2 nodes at the median. Push the median element up to its parent node. If the parent node also contains M-1 number of keys, then split it 2 by following the same steps. Okay. Now coming to the deletion part. Deletion is also performed at the leaf nodes. The node which is to be deleted can either be a leaf node or an internal node. Following algorithm needs to be followed in order to delete a node from a B tree. First, we have to locate the leaf node. If there are more than M/2 keys in the leaf node, then delete the desired key from the node. Third is, if the leaf node doesn't contain m by 2 keys, then complete the keys by taking the element from 8 or left sibling. So, if the left sibling contains more than m by 2 elements, then push its largest element up to its parent and move the intervening element down to the node where the key is deleted. Again, if the right sibling contains more than m by 2 elements, then push its smallest element up to the parent and move intervening element down to the node where the key is deleted. So coming to the fourth step is, if neither of the sibling contains more than m by 2 elements, then create a new leaf node by containing 2 leaf nodes and the intervening element of the parent node. And if the parent is left with less than m by 2 nodes, then apply the above processes on the parent too. Now, coming to the application of B-tree, B-tree is used to index the data and provides fast access to the actual data stored on the disks. Since the access to values stored in a large database that is stored on a disk is a very time-consuming process. Searching an unindexed and unsorted database containing n keys values needs O(n) running time in worst case. However, if we use B-tree to index the database, it will be searched in O(log(n) time in worst case. Now, final one is B+tree. So, B+tree is an extension of B-tree, which allows efficient insertion, deletions, and search operations. In B-tree, keys and records both can be stored in the internal as well as leaf nodes. Whereas in B+tree, records can be only stored on the leaf nodes, while internal nodes can only store the key values. The leaf nodes of a B+tree are linked together in the form of a singly linked list to make the search queries more efficient. B+trees are used to store the large amount of data which cannot be stored in the main memory. Due to the fact that size of the main memory is always limited, the internal nodes keys to access record of the B+tree are stored in the main memory, whereas leaf nodes are stored in the secondary memory. The internal nodes of B+tree are often called index nodes. A B+tree of order 3 is shown in the following figure. So, coming to the advantages of B+tree. So, what are the advantages mainly? So, records can be fetched in equal number of disk accesses. Height of the tree remains balanced and lesser compared to B-tree. We can access the data stored in a B+tree sequentially as well as directly. Keys are used for indexing. The fifth one is faster search queries as the data is stored only on the leaf nodes. Now, finally, coming to the B-tree versus B+tree. These are the differences. So, first one is, some keys cannot be repeatedly stored. Redundant search keys can be present. Second is, data can be stored in a leaf nodes as well as internal nodes. Data can only be stored on the leaf nodes. Third is, searching for some data is a slower process since data can be found on internal nodes as well as on the leaf nodes. And searching is comparatively faster as data can only be found on the leaf nodes. Then deletion of internal nodes are so complicated and time consuming, and deletion will never be complex process since element will always be deleted from the leaf nodes. And the final one is, leaf nodes cannot be linked together, and leaf nodes are linked together to make the search operations more efficient in case of B+tree and B-tree. So these are some differences of B-tree and B+tree. I know this is a very lengthy video, but the topic is also much more than expected. That the B-tree, I have explained all the types of tree in a detailed manner. If you guys follow this video and if you guys follow just PPT to remember, so it would be enough for your exams, I can say confidently. Okay, so in the next video we will learn about the graph. So see you next time.